Thanks for the opportunity to speak here. The talk will not have a punchline. It's going to be like a hodgepodge of some ideas. I mean, the main thing is to bring into place two concepts that haven't been discussed so far, which are related to trying to understand the bulk, and might be useful later on. But I mean, definitely there's been a lot of work about the bulk. Thomas talked about it. Hermann in the higher dimensional case. But there are some players that didn't show up that much in that discussion, so I'd like to spend some time on those. This is based on work done with a lot of people, and the papers I'll focus on are these papers. Okay, so okay, why is double-scaled SYK interesting? I'll give you my perspective. Then, you know, how do we write a path integral for chords, and what's the relation for with the transfer matrix? The fantasy is that I mean, this is going to be a completely well-defined path integral. It generalizes the G sigma, but it doesn't have any divergences or any ambiguities or any contour issues. So you can fantasize that it might be useful for something. To be honest, I don't know what exactly right now, but maybe. Then I'll talk a little bit about the bulk and some issues, and then how do we think about the system as a non-commutative space-time? That's also something that's kind of lurking in the deep, but hasn't really shown up in actual computations that much. And then I probably won't have time to get to this, but maybe I will. Okay, so the SYK model is useful in condensed matter. It actually started its life in nuclear physics, and of course we are excited about it because of the relation to string theory via the maximal Otok, Kitayev's computation. The double-scaled SYK model is, if we denote the length of the interaction by p, the double scaling limit is take n to infinity, keeping p squared over n, which I'll denote by lambda, keeping this ratio fixed. And a parameter which will be important is q e to the minus lambda. Now, what makes this model interesting is that it's kind of very, very universal to just about any p local interaction that you will take. So, for example, a model that's been studied a lot in the spin glass literature is something like, you know, take a bunch of take n copies of the spin 1/2 representation of SU2, and have your Hamiltonian be a sum with random coefficient over chains of length p of Pauli matrices. So the double scaling solution of this thing is the same as the SYK, the double scaled SYK. Even though at finite p this has very, very different and interesting spin glass, is supposed to have very interesting spin glass dynamic, which replica symmetry breaking, and there's I should say, you know, if people are interested in relation to spin glass, there's kind of an issue in spin glass physics, which is what's the long time behavior. There's certain hierarchies of energies. If you're above some gap and you're not sitting in one of these very deep minima, there's a very long time dynamics, which has been studied, but it's kind of interesting to see whether that's related to any of the long time dynamics that we're discussing. So it's kind of interesting that this applies to many models. And of course, p locality is generally an important principle because, you know, it relates to, you know, if there's ever going to be a quantum computer, you will act only on p of them at the same time. This is like a grant state sentence for people who've been writing grants. Okay, a little bit more interestingly, kind of conceptually, is that in two-dimensional gravity, we usually study dualities to models that have full unitary symmetry on the Hilbert space. So it's kind of a Wigner-Dyson example. The JTSSS is, I think, the prime example, prime recent example in our field, and many generalizations. It works very well even in the non-perturbative level, and there are many techniques. Essentially, like tooth double line is what we're familiar with, but you know, all of these are versions, elaborations, ingenious elaborations on it. It becomes tricky at the multi-matrix level. It becomes even worse when you try and add probes to this theory and compute something like an OTOC, or generally just match the dynamics of probes to that of gravity. This is a personal take. Other people will strongly disagree with this statement. Other people glaring at me from the audience will strongly disagree with this statement. And the reason is like this, you know, this is essentially our model. DH is a dimension of the Hilbert space, but then I do some multi-matrix model in order to add some additional probe. These are my observables. To leading order in 1 over DH, what I'm allowed to do, I'm always allowed to contract matrices up to vertices, contract the symbols up to vertices. But the rule is that I'm never allowed to have contractions of Hamiltonian or any of the probes if they sit in the standard ensemble. I'm not allowed to have the contraction intersect. Instead, I can have vertices. Now, this is very different from the chord construction that I will present, where the whole thing is because you can allow these contractions to intersect. You can fudge this. Because in principle, whenever you have, say in my language, contraction that intersect, say, you know, 2 chords intersecting, you can replace it by a 4 vertex, but you kind of lose predictability very quickly. You know, people who are interested in, you know, what can you say about this, you know, correcting this order by order, and what's the size of these vertices? There's some recent work by Kurchan, but also people in our field. So you have to kind of pick your poison. You either work in the theory that has only gravity, which is this Wigner-Dyson ensembles, and then there are lots of techniques, or you can work in a model in which there are particles and the right OTOC, but then none of the techniques apply. In particular, if you ask about corrections to say multi-boundary you know, configurations, then the usual machinery of topological recursion relation and bulk geometry doesn't really work. Okay, so it's kind of, you know, there's a reason why we kind of want to stick with SYK as it is and not go to the SSS limit, type limit. Okay, finally, I should say that this also applies to, there are also non-p-local versions that are solved by code. Actually, one of them is, I mean, the classical one is the Parisi hypercube. You basically have d dimensions. You have 2 possible states in each direction, and you hop, and there are certain magnetic fluxes on each of these plaquettes. So as you go around the loop, there's a frustration in the theory, and the Hamiltonian is mixing. This was actually solved by Parisi a long time ago using essentially codes, basically. Okay, and this is a non-local, of course, as you can see, it's non-local. All the terms, the positions, all the, you know, state of the entire system is important for every hopping. Okay. So let me just summarize at least what I've been looking at. So we can solve this exactly in this parameter lambda at a null energy scale in the limit n going to infinity. The OTOC looks like some power of lambda to some power e to the chaos exponent. Usually we are used to having 1 over n there, and we are used to 1 over n as being something like 1 over m Planck, some gravitational interaction. So lambda replaces 1 over m Planck, and if we solve for all values of lambda, it means that we essentially solve for exactly in m Planck. That's, one needs to understand better the bulk to see whether that's a correct statement or not. But definitely lambda sets a kind of shortest distance in space-time. So lambda times the ADS radius, if I'm going down to the ADS regime, is the shortest distance that you can probe. And you can see this in many ways. So we have a theory that naturally has a kind of a UV cutoff. And we'll see that many UV divergences disappear. I mean, that was already, I think, in Thomas's talk that, there's going to be a maximal energy, and that helps regulate many UV divergences. Of course, we can get the ordinary JT gravity in the infrared if you take lambda to 0. Okay, but then what's really interesting is that there's a very rigid algebraic structure. The SL2 that governs JT gravity is replaced by this non-commutative quantum group. And what's a little bit bizarre, or kind of natural once you say the statement, but kind of a little bit bizarre if you're doing gravity, is that space-time becomes a non-commutative ADS2. So, and then you have to start thinking about, okay, what does that mean exactly? What model can I write for a space with non-commutative coordinates? And I'll discuss this a little bit. And of course, there are many applications to quantum chaos. And from my perspective, this non-toothed way of getting two-dimensional surfaces is very interesting. Let me maybe say something about this for a second. So, saying this again, just rambling off. If you discuss algebras, the von Neumann algebras and all of that, the whole discussion is when I take large n limits, what kind of algebras can I get and what can I say about them? That has become kind of an essential question in our field, and of course there's the different type, the classification, different types. This notion of freeness, which is equivalent, so mathematicians came up with the notion of freeness in algebra, and that's equivalent to saying that you're taking the limit in a way that lands you on the Wigner-Dyson ensembles. They didn't appreciate that at the beginning, but it turns out that it's equivalent. And this is a different way of doing it. So presumably there could be many different ways of taking large n limits. SYK is the simplest one, which is non-trivial. And then each of them will give you a different kind of algebra, and it's kind of interesting to see whether these algebras have any relation, or they give you more information about the algebras that you might see in gravity. Okay, so, okay, but let's talk a little bit about the nitty-gritty details. Okay, so of course the statement is that if I take SYK, I compute trace e to the minus beta h. These brackets, subscript j, means that I'm doing the ensemble average. I can expand it, or I can write it as a path integral by kind of splitting it, which I'm going to do in a minute. And then the statement is that trace h to the k averaged over j. I also normalize the trace such that the trace of the identity is 1. So this differs by 2 to the minus n from the usual trace. So the statement is that this trace is the sum over chord diagram, q to the number of intersections. And q is e to the minus some constant that depends on the model times lambda, or p squared over n. So what's a chord diagram? I take two k points, I take k points on a circle. K has to be even for this to be non-zero. And then I just look at all the pairings between them. So if I compute trace h to the 4, there are these 3 pairings. This one has an intersection, these guys don't. So the sum is 2 plus q, and this is the partition function at large n in the double scaling limit. So what I'm going to talk next is kind of how do you write a G sigma for chords, or a path integral for chords, and then briefly about the transfer matrix. Of course, if there are any questions, feel free to pause me anytime. Okay, so in the double scale, this SYK, this power of q, right? Every intersection has q. So if a diagram has this is q versus this guy, which say I normalize this to 1, so this is going to be q. And the reason is that when I pass them across each other, so I want to see what's the what's the relative strength of these two diagrams. And of course, these guys go off to some other regions in the core diagram where they contract with other points. Then this guy equals this up to -1 to the number of sites that overlap. So this I is a sequence of length p of integers drawn from 1 to n. This is the coefficient. This tells me what's the operator that I'm inserting from the Hamiltonian, which of the operators. And when I try to commute them, so I, j and ij prime are two sequences of p numbers, each drawn from 1 to n, and there's some overlap, and this overlap has some Poisson distribution. So what I need to compute is the average of this -1 to the size of the overlap in the distribution. Yes?
Just a question about, I guess, the previous slide. So whenever you draw diagrams, the rule here is that you always have to draw the diagram with the least amount of intersections?
No, all intersections.
No, but given a configuration of, given a set of weak contractions?
So I don't allow double contractions, right? So really a contraction between two lines is just if they are kind of ordered or disordered or autoclike.
Yeah, what I mean is that given a given weak contraction, you should always pick the least amount of intersections, right? Like, I don't know, for example, the diagram on the left, you don't allow
I don't allow double intersection. So I don't want to draw a diagram where this goes like this. Okay, but that would be a double intersection, and I don't allow it. Well, it's not that I don't allow it. I mean, basically the notion of intersection is just determined by the ordering of the points. So there's no ambiguity in it. It's not an issue of drawing.
Thank you.
But this will come back to bite when we try and talk about the bulk. So this is, you just compute the average of all the penalties that you pay when you move lines across operators across each other. In the p-spin model, you can easily convince yourself, there are n sites, so you just ask, what does each of the sites do across the chain? If it's not, or if they are uncrossed, then you get one version of the trace on this small Hilbert space. If they are crossed, you get another version, and these guys are different. In the Parisi model, it's really the simplest because a chord means that you've gone in some direction to the other dot, which basically means that if you have a chord and then another chord, then you've gone a direction, gone back, gone in another direction, come back, so you don't pick up any of the holonomies, but if they are crossed, then you pick up the holonomy of the plaquette. So the Parisi model is somehow the most straightforward to see this picture. So how do we write a path integral? So there are really two length scales in the problem, if you want to kind of think physically. So there's the scale of beta. I'm computing e to the minus beta h. That sets the largest length scale in the theory. And then there's lambda, which in terms of size, it's lambda times r radius. This is the shortest length scale. It's associated with starting to see that space-time is discrete. You're kind of working at the level of each time a single chord. And we want to work somewhere in between. So, the formula that I'm going to write is an exact formula, but it's convenient to think about lambda as being small. In this case, we split the thermal circle into intervals, and the degrees of freedom are how many chords go from one interval to another. I split it into intervals. This is the I interval, this is the J interval, and there's Nij chords that go between them. And of course I do this for all other intervals. So this is going to be some NKL. So it's very easy to extract the number of intersections in using this parametrization. And you can write an exact formula. And these exact formulas rely on the fact that, whenever you cross, there's a factor of Q. So when you do sums over permutations, there will be weights of Q. But you can write an exact formula summing over all of these Nij's. These NQ factorials are just a product of one Q up to NQ. And this is what's called the Q number, M.
Okay. How does it scale largest length scale with the number of fermions, or?
This is essentially the number of fermions n went to infinity, and the only remnant is Q, which is e to the minus p squared over n. So I've taken the large n limit already. Okay. And of course, this is the partition function when in the normalization when trace of the identity is 1. So in physicist normalization, there's going to be another e to the 2n, e to the, 2 to the n over 2 or 2 to the n, depending on which model exactly I'm doing.
So why in that limit there is a largest length scale? I don't see.
Well, I kind of think about, I'm doing the Euclidean path integral, so there's a circle of size, of physical size beta, and that's it. I mean, you can of course do like Keldysh contours that go out and come back, but you can do that. Okay, so this is an exact formula for any value of S. It's completely well defined. There are no divergences. There's no issue of contours, and it starts to look a little bit like some kind of bulk or boundary term. These terms have to do with these kinds of intersections. Like this that sit in the interior, so they are like bulk terms of some sort, and this guy essentially product I going from 1 to S goes in the continuum to some kind of integral over the boundary. Okay, and okay, I'm not going to do the proof, but it's very simple once you get used to some of this Q gymnastics. You can now, if you want to think about this as being familiar to maybe something that we've seen before, I'm going to take lambda to 0 to go back to the ordinary SYK limit. And I want to keep beta fixed, so I can put many intervals. I'm going to take S to infinity and lambda to 0. And then I need to rescale this, and then the action has some continuous, goes over to some continuous variables. Yes?
Sorry, just a quick question. When you take lambda to 0 after taking the double scaling limit, can you think of that as an ordinary finite P? You cannot think of that as an ordinary finite P SYK. It's like a large P limit of SYK.
This is the large P limit of SYK. In the following sense, I mean, many of the formulas written for large P limit SYK will just correspond to taking the lambda equal to 0, and then at the end of the day just truncating that, and at the end of the day just plugging lambda equals P squared over n. Then you will end up with the large P formulas. This is point 1. Point 2, there is some formal sense in which you can write the large PG sigma, I'll get to this in a second, expand it, rewrite the expansion as chord diagrams, resum it, and land on the double scaled SYK. But that requires expansion and effectively rewriting it as a chord diagram, and then you get chord diagrams.
So once you start with a double scaling limit, there is no limit you can take to recover ordinary SYK.
The finite P, no.
Okay.
No. Yeah.
Thank you.
I mean, that's why this problem has been annoying me for some time, which is how do you see the spin glass phase in this kind of model? But if you're familiar with this long time behavior discussion in spin glasses, it also tells you that maybe that long time spin glass behavior in an appropriate large P limit goes over to something like a Schwarzian or a generalization of the Schwarzian. So all of those might be conceived, I mean, it would be interesting to see if all of those are like some controlled deformation of the Schwarzian. So can you do a 1 over P expansion after you've taken the double scale limit? Okay, so you can write, okay, so this is an action, fine, you know, it's like a non-local weird action. You can write the saddle point equation of that. And at this point, I'd like to remind you that the G sigma for large P SYK, exactly what you were asking, has this form. And you can either do saddle points or expand, or but this essentially has some problem that it's not bounded from below. However, you can write the saddle point equation, and if you define my variable n to be the second derivative of g, so n is the second derivative of g, so this just becomes g. This becomes log of the second derivative of g. So you get this equation, which is the same as this equation after you exponentiate and correct for all the signs that I typed wrong in this. However, again, this is not a completely well-defined action. It's solved by expanding either saddle point or expanding e to the g and choosing a specific propagator which turns it into chords, which means you have supplemented it by some kind of contour prescription, which is not completely well understood, but you're back to chords basically. Okay, so this is useful as a starting point for generalizing the model, and you can fantasize maybe this is useful for understanding the bulk. So let me just jump ahead a little bit. And then I'll go back. So why do you think this is this might be useful? So working the beta going to infinity limit. So we have many chords because we take e to the minus beta h, which is a large beta. So we need to expand this to a high order. So we have many chords. And then we take q to 1. So there's not much penalty when chords cross. So chords can go a long distance in the bulk. And what you get is a picture which becomes kind of denser and denser in the bulk, basically. And you can fantasize that this is kind of fills up the ADS2, the Euclidean ADS2. In a sense, this is what Lin and Stanford do. They take exactly this limit of a very long, you know, a string whose size is goes such that the number, well, they essentially look at very long, they look at a configuration, at a slice, which many chords cut. And the number of chords that cut it go like 1 over lambda. And then you can think about that as the physical length being fixed. I'll discuss this a little bit more later, while taking lambda to 0. So it's exactly this limit, and you can basically reconstruct physical distances in space-time in this way. So this is kind of the picture. It's a little bit, you have to be a little bit more careful, but essentially this is the machinery that goes into staying away from the Schwarzian limit, which is the finite beta. But I think it would be interesting to understand how you manage this Euclidean, funny Euclidean path integral. It's not really known yet. So again, I warned you, I'm going to just throw some stuff which is out there but hasn't played a big role so far. Okay, I want to talk for a minute about the transfer matrix. So we have this chord diagram, and we basically need to find some useful technique to evaluate it. And that's basically done by the chord diagram. You cut it somewhere and you start, say, going counterclockwise, and each time you can kind of sprout a chord or absorb a chord, okay? So this diagram is, when I go linearly, becomes this, and this is just a very simple linear process where I either add the chord, and I'll have a convention where I add it below, or you contract a chord, and then you can contract any of the chords above. And basically, I'm just going to accumulate the weights as I go along. So, okay, you have to define exactly what does accumulating the weight means, but essentially, a process like this means that, you know, here I go from L-1 chords to L chords without adding any intersection. So if I'm asking what are the weights here, I can just copy what I had with L-1 chords. And this thing means I'm going from L+1 to L, and then I can contract any of these guys, so I have this coefficient. So this iterative process, the transfer matrix, is just given by this, and I can arrange this in a matrix. And this is an amusing matrix. It's what's called the Harry-Kuhn Q-deform. It's based on the Harry-Kuhn Q-deformed oscillator algebra. I can take A, the annihilation operator, to be this line, this diagonal, and A dagger to be this diagonal, and then you satisfy this Q-deformed algebra. Okay, so there's a factor of Q here, which you need to take into account in computations. So that's like the first glimpse that you have some non-commutative geometry lurking here. Now you can see, I'd like to just, you see I wrote A and A dagger here. They are dagger of each other with respect to some non-trivial norm, which I'm going to get to in a second, which is a little bit painful. But of course I can conjugate this matrix to something that is Hermitian in the ordinary norm. But it's important to keep track of this norm for reasons that I'll discuss later. Okay, the point is that we know everything about this operator T, and essentially it means that trace e to the minus beta h evaluated going through this chord trick means that I start at 0 chords, I do this process with T, and I end with 0 chords. So this is the expression. So you've kind of kept a minimal set of correlators while coarse graining over everything else. That's what this algebra business is supposed to buy you in general. And then any insertion of e to the ith can be replaced by e to the it times the transfer matrix. So the transfer matrix is my new Hamiltonian, and it works in an auxiliary space, which is the space of chords, the number of chords. And this will translate into length of slices. Say if I do if I quantize JT gravities, I mean, Thomas discussed how that works exactly going the other way. And the point is that this goes over to the Schwarzian at the Q going to one limit when I go to the minimal energy in the system. So I just want to remind you how we kind of see that we have space-time. So let me remind you that the whole business of JT translates to the dynamics of the boundary particle. And which is essentially given by this Hamiltonian after you choose a specific gauge. You can do this in Euclidean, you can do this in Minkowskian, and there's an additional condition here that the trajectories go to infinity and end in infinity. So you come back, you start under the potential and you end under the potential, and you can argue very simply that this is. Okay, I'm not being very precise here, I'm being very, very loose here. You can argue that this is what you get from the transfer matrix. You can arrange conjugate the transfer matrix to this form, and then you see if you go down, which means very, very large distances in space-time, essentially you have one above and below the diagonal, up to a constant that's like a second derivative. It essentially becomes like a lattice model on a ray, just a one-sided lattice model. If you look at the ones and you go down the diagonal, you just get a second derivative. And then if you ask about this q squared, if you define e to the minus phi as e to the minus lambda n, this phi is really some distance, if you track the Jafferis-Harlow or the Altan-Bagretz-Kamenev, this is just a distance. If you define phi to be minus lambda n, you see that what we call e to the phi in ordinary JT is just q to the n. So if you go way down and you think about this expansion, you exactly get the Hamiltonian that we're used to. Okay, this we've seen before. So we reproduce spacetime, but let's discuss a little bit some of the subtleties. So the problem, one subtlety, which is a little bit less of a subtlety, I think, but is something like this. You know, suppose I give you some chord diagram, okay, and it gets denser and denser. So let's just look at the intersection of three chords, okay. I can move this chord, you know, so say, you know, okay, let's say this chord, this yellowish is this one, and these two are any of the other intersections. Okay, so I can move this chord to be above some intersection or below some intersection. So I can't identify intersections with points or exactly with volumes per se, because I can kind of move. So, you know, if you insist about thinking about this as a little piece of volume, then it's like pieces of volumes floating around and you can kind of rearrange them, but that's just a bunch of words. But I think it's fair to say that this is a kind of obstruction at the microscopic level. If you have a diagram that has many chords in it, you can show that the amount of ambiguity relative to the amount of chords that you overall have and their various arrangement goes to zero. So in some sense, there are some global constraints coming from the fact that you can't intersect twice that tell you that this kind of ambiguity is not as bad. And what it seems to do is that it gives you an ambiguity on an ADS radius scale. Okay, so if you are at very large beta, you're fine. If you are at very small beta, and you want to think about this as geometry, which you may not want to do, then you know, there's some fuzziness. You start seeing the fuzziness. If you want to be a little bit more precise, well, again, I mean, the problem shows up again. So remember that I told you that I have some chord diagram, so I can count the number of chords at each, the height of this diagram at each moment in time, and I'm going to call this the envelope of the chord diagram. If you trace through what I said before, that phi is like a coordinate on ADS, it's essentially some specific slicing of the Euclidean disk, then you can map this thing to some geometry. Well, I mean, like you can think that you can do it, but if you map this to some geometry and you compute, say, the distance between this point and this point, you will see that there are, on the saddle point, this will agree with what you get from ADS2, but away from the saddle point, these distances will just be very different. So it's not that you ever have a consistent geometry that cuts off a space, cuts off part of your space. Okay, so there are different chord configurations that give you the same envelope, but then there are issues. If you cut it in a different place, you get different envelopes. So you don't really have geometry. And that's because these degrees of freedom somehow sit below what we call the usual gravitational one. And I think it's kind of conceptually interesting, but of course, practically I'm not sure what to do with this. But weights on envelopes are well defined. If I assign some weight to envelope or to a chord diagram, that transforms well, and it's kind of related to why you have non-commutative geometry. Let's see, yeah, okay, I want to maybe just spend a few minutes on this guy. So you can get more information if you add more probes. There's a kind of universal model for the probes, which is again the same throughout all these models that I discussed. Essentially, you just add chords with some different color, and different rules for, you know, what's the weight of an intersection between a probe chord and a Hamiltonian chord. And that's a very general construction. It's actually known in the math literature. It goes back to the work of probability theory / algebra person called Speicher. You can compute the 4-point function, and you see that it's a 6J symbol of SL2 q to the 1/2. For some reason that I don't understand, it just comes out of the computation. However, there is one thing, like, you know, before I define the Hilbert space as the number of chords, now I need to define this interim Hilbert space as a configuration of chords of different colors. So H are the Hamiltonian chords, but then I put some particles. So this is my configuration. This is a much more complicated Hilbert space, and the inner product between this Hilbert space is I give you one state given by some ordering of dots with colors and another one, and the inner product is do all the pairings, sum over all the pairings such that, you know, the same colors are paired, q to the number of intersections, or the appropriate q that has to do with the intersections. Now, unlike the case of a single chord, we do not know how to turn this into an inner product which is diagonal, which is just the identity essentially. Like, I mean, that might be a technical issue. I mean, one can think about ways of remedying this. But it has an unpleasant consequence for trying to give, I mean, one has to worry, if one chooses to worry about this, that the notion of Cauchy slices becomes a bit fuzzy in this model, because Cauchy slices means basically, let's take by space, do some states preparation here, Euclidean, Minkowski, whatever you want, do some preparation here and glue them, okay? Now, when we do this, in double scale, we prepare a state here, we prepare a state here, but the inner product has intersections in it, okay? And the intersections, I told you, if you remember, these intersections were like, I wanted to think about them. Of course, all of this is biased because it goes through some layers of interpretation. These intersections set in the bulk term of the gravitational action. So really the inner product takes over a little piece of your bulk action, whereas you usually want to think about this inner product as just gluing two Cauchy surfaces and doesn't eat any of your action. At least that's the way I think one wants to think about Cauchy surfaces. But here it doesn't quite work this way. It's like you really can't separate this, and so somehow this notion of Cauchy surfaces in space-times become a little bit questionable, and that's kind of very. I mean, it's not that it's exactly the same effect, but you see some remnant of this in this fake disk, for people who know, where your physical region, the in-state is one potentially tiny chunk of some reasonable space-time, and the other out is yet another, and the gluing between them is, okay, just some, you know, it's not exactly clear where you're supposed to put a Cauchy surface in there. Like the Cauchy surface jumps in what you would think of as a smooth space-time. So this is something which is you need to worry about, even when you take Q to 1, but you're working at finite temperatures. How much time do I have? 1 minute, so I'll talk really quickly. Yes, okay. Let me just say about this, just flash, like just throw some yet formulas at you. So SL2Q is this algebra. Essentially, if you think about SL2 and you have these generators, which I'll call L0, E, and F, then K is Q to the L0. L0, for my purposes, is something like just the smooth dilatations on, say, the Poincaré patch. And so the basic statement is the following. Like, we know that the boundary particle is in SYK is the following thing. Choose a point, look at all trajectories that start and end in that point, and give them some weight. Since all of this is SL2 invariant, the weight that you give is just given by the Casimir of the representation. So instead of looking at trajectories, you look at wave functions. The wave functions transform under SL2, and you propagate them with the Hamiltonian, which is the Casimir of that representation. That statement is true here. You can show that the transfer matrix is a Casimir of SL Q to the 1/2, acting on a bunch of representations. So really the group theory definition of this non-commutative version of ADS2 is I chose a specific set of representations to describe the boundary particle. And if you want to add a particle, you may need to add some other set of representations and maybe some interactions between them. And then you can show that the transfer matrix is just this Casimir. And if you want to be a little bit more precise, you can essentially write specific models for ADS2 using coordinates which are non-commuting coordinates. So here I gave the example of SL of three-dimensional ADS3 because that's our starting point. We then do reductions to ADS2. But this is usually de Sitter, three-dimensional anti-de Sitter. These are ordinary coordinates. When you go to non-commutative geometry, you have these relations. The coordinates no longer commute. Your functions are polynomials in these symbols, etc., etc. There's a non-trivial star product, etc., etc. But you can do the reduction and see that you exactly get okay, so this I'm not going to do. Okay, so I mean, there's this path integral, there's this, so the three things I wanted to kind of emphasize. There's this path integral, which is well defined, looks like it wants to give you some space-time, we don't know how. When you try and slice it to discuss, you know, Cauchy surfaces or time evolution, there are some, at least at this level, conceptual puzzle. In terms of computation, you can compute, and these conceptual puzzles translate into very funny behaviors of geometries. And finally, there's this non-commutative geometry, which is there, but it's, you know, should reflect the two earlier problems, but we don't even know how that works. Okay, so let me just summarize. These are not ordinary Wigner-Dyson ensembles. You know, there's a very rigid algebraic structure, which is very interesting. One more minute? Okay. Let me emphasize this point. So, okay, so we've been talking a lot in, we've been talking a lot, excessively, some people might say, about the ramp and the plateau in coming from two-dimensional gravity. These terms are always there in any chaotic system that is not too fine-tuned. I mean, now, but where do physical systems differ from each other? Where do chaotic systems differ from each other? They really differ from in the behavior here. So this is still the spectral form factor, but the connected piece. It's not that this is the disconnected piece, which is fine, like nobody cares about that. So real physical systems differ here, okay? So pure Wigner-Dyson ensemble will just have this, you know, maybe there are some bumps here depending on the... Now, SYK has, double-scaled SYK has this behavior. So really the notion of taking, if there is a classification of how you take different large n limits in matrix theories, it will really teach you something about this region, which has been considered non-universal until now. But maybe there is some universal structure in this regime, which I claim is a little bit more, just a tiny bit more physical. So I think this is a challenging problem, which is why I'm kind of interested in just understanding how you take large n limits and their algebraic properties. Okay, quantum gravity regime, I pontified about that, and this is the point that I didn't get to. Okay, thank you.
So maybe while we change, we have time for one question.
Yes.
So, can you use the non-commutative? I know you said there are questions about non-commutative geometry tree, but can you use the non-commutative description in Lorentz signature? It's often said that non-commutative field theories, for example, don't work quite nicely in Lorentz signature. This is not a field theory, but does it? What can you say?
Well, I mean, it's a little bit even worse in the sense that the model that we have is such that if you do normal evolution of wave functions on that model, you reproduce the boundary particle. Mm-hmm. Okay, now the boundary particle, if you remember, has a very large imaginary magnetic field. So the notion of signature there is kind of questionable anyhow. When you do the reductions from ADS3, as these guys did, it's some null reduction, which you need to be careful about. I mean, I think we need a few more building blocks in order to see that. We haven't done that much work on this, but I think the answer is going to be yes, because analytically continuum, because the spectrum is bounded, analytically continuum from e to the minus beta h to e to the ith, there's no issue there. So the model should work similar, yeah, but we're not at that stage. Okay.
I have a question. The core diagram that you presented are somehow related with the core diagrams entering the theory of Vasiliev invariant for knots? Are the same? There is a relation?
I think Hermann is more qualified to answer that question, since he's working more on the three. I don't see a direct relation, but because it's not it's SL2, not the ordinary groups discussed in knot theory, and Q doesn't always agree. But I think Hermann thought about these issues. I mean, that's kind of Hermann's research project, basically.
No, the only thing I can say, I guess, is that there's a sort of a scheme, or at least something like the same kind of knot relations that people have identified in these kind of invariants do appear in here.
In SL2, with proper quantization.
But
it's not literally related to the chords. There's still a non-trivial mapping.
I have another question, because you presented the transfer matrix, but you didn't present R matrices or braid matrices of these. And the other question is the following. You have only one parameter Q entering, and at a certain point you presented the Aric-Kohn deformed oscillator. Do you have only one pair of the deformed oscillator, or can you have more?
Okay, so if you add these additional particles and you give different weights, then you have more. You can have as many as you want, basically. Mm-hmm. So these additional particles will translate into additional pairs of like what I said before, basically. And also, like, between them, there will be non-trivial Q commutation relations.
And you can have different Qs as well?
Yes, yes.
Right.
One question still, Micha. So you mentioned the quantum group. You wrote down the quantum group relations.
Mm-hmm. Right.
Maybe you or Thomas have already said something about this, but the quantum group, as far as I know, doesn't literally act on the double-scaled Hilbert space. You need to do a constraint. At least it's only part of it that actually works on it. Is that correct?
So
you mentioned the Casimir, but
Okay, so it doesn't act on the chords, but it acts on this model of non-commutative ADS2 that I had. So these guys, well, okay, I'm not going to. I mean, if you remember, I had these Z and H coordinates. SL2Q acts on them.
Yeah, but I thought that the operators that you have in double-scaled SYK are a subset of the operators that you can get out of the like a Hamiltonian reduction type.
Yeah, I mean, they don't act directly on A and A dagger. They act on some gauge. I mean, A and A dagger come after some kind of gauge fix.
Correct. Okay.
But it's an issue of okay, so if you go to Princeton, they will tell you that there is no SL2 unless you do the two-sided version, which is true. But then I anchor it at one point and do some stuff, and there's obviously a meaning in which I can still think about SL2 as acting on the non-linearly or something on that thing. Yeah.
Okay, let's thank Micha again.
Thanks.